Now this video I'm going to talk about a second specialized case unique to Chemistry 1, and this is the concept of finding the delta H of a reaction in a water calorimeter. Now again, I don't like videos like this because they give you a very specialized problem that you're not going to find broad applicability to, but they are the types of problems we solve at the Chemistry 1 level. So in this video, we're going to look at a heat of reaction. Now specifically, we're going to look at the heats of dissolution because this is the easiest to measure in a calorimeter, although you could do a neutralization reaction as well. The point here is that you have your calorimeter. It has some mass of water in it, but now we actually have a reaction running. And so for this one, we're going to look at lithium bromide, solid, dissolving to lithium and bromide. But this could be any reaction. So how do we solve this? What type of questions can we ask? Well, a big one we'd like to ask is, what's the delta H of dissolution? So to answer this problem, and to answer any problems related to reactions with calorimeters, we need one relationship, and that is Q of the system equals minus Q of the environment. Because we have to describe how the heat is being gained or lost by each side of this. So in the case of the water, Q of the environment, particularly with this chemistry level, we're going to have the mass of the water times the CP of the water times the change in temperature of the water, which we can represent mH2O dot CP H2O times T final, and we'll use Ti for the water. Now, unlike problems where we're being asked to work with the CP of whatever's in there, so in the previous video we worked with the heat capacity of the metal. The Q of the system is going to be in delta H of reaction. Now, what we're looking for here are moles of one reactant, and we're going to need to specify that when we looked at the units on delta H. So it's going to be, ultimately units of delta H can be kilojoules per mole, whatever we're looking at. Ideally, we would actually work with moles in terms of an extent of reaction. So we would find what the extent of reaction was and just divide by that instead. But for simplicity, particularly at this level, we're only going to focus on moles of a reactant. In this case, how much lithium Br was dissolved. So here's the actual problem statement. We have, sorry, I got to read off a sheet to you. 100 grams of water, 10 grams of lithium bromide, LiBr. The starting temperature of the water is 21.3 degrees C, and when it finishes, it's at 34.7 degrees C. And what we are trying to find is the delta H of dissolution. So this information should have popped up on the screen, so this way you can pause the video and write it down. How are we going to solve this type of problem? Well, we're going to use these relationships. We have the Q of the environment, it's the mass of the water, times the CP of water, times the final temperature minus the initial temperature equals the negative there in delta H of dissolution. So this problem, we're being asked to find the delta H of dissolution, so this is what we need to isolate. When we move it all over, we get the mass of water, CP of water, final minus initial, all over negative N. Now, a few points to note here. The water got hotter. So if the water is getting hotter, this is an exothermic reaction. We expect the sign on delta H to be negative when we finish for an exothermic reaction. Conversely, if the temperature had dropped and we had an endothermic reaction, we'd expect the sign on delta H here to be positive. And this is something to keep in mind. Make sure your delta H's make sense in terms of what you're seeing. If the calorimeter is getting warmer, it's exothermic, the delta H should be negative. If the calorimeter is getting cooler, the delta H should be positive because that's an endothermic reaction. But from here, we can just plug in numbers. The mass of the water here, 100 grams. CP of water, 41.181 grams per degree C. The final temperature here is 34.7 degrees C. Initial temperature is 21.3. Now, as for the moles, this N number is going to come from that 10 grams, but we had to convert to moles. So, lithium bromide, I have the molecular weight here is 86.84 grams per mole. So if we convert that to moles, we had 0.1152 moles of lithium bromide. Now, you're typically going to normalize to whatever is one of the reactants. So if you had two, let's say you have a neutralization reaction, HCl and NaOH, you want to normalize to 1. You don't want to normalize to moles of everything, just moles of one thing. So when we finish working this out, for those of you playing at home, we get minus 48.83 kilojoules per mole. lithium bromide. But if you work this out, you probably actually got 48,830. Delta H's are always reported in terms of kilojoules per mole, not joules per mole Kelvin, because the world operates on kilojoules. So when you finish this problem, if you end up with something like minus 48,830, which is what you're going to end up with these numbers, that's because this 4.18 is in joules. So you need to divide by 1,000 to get you out of joules and get you into kilojoules. And that's how you work these types of problems.